Bismillahirrahmanirrahim. Electrical network analysis. And today our topic is RC transient discharge phase. In the last lecture, we have studied the charge phase. In this phase, in this lecture, we will study the discharge phase for the RC circuit. Okay, so this is the first example for the RC circuit of the discharge phase. Okay, so we have to find the VC, voltage developed across the capacitor, the current through the capacitor, and voltage drop across the resistor if the switch is just closed at t is equal to 0. Secondly, we have to plot the VC versus the time, and we have to find the VC versus the time constant tau. Okay, and similarly we have to plot the IC and VR versus the time constant tau. Okay, and we have to find the values for the VC at t is equal to 20 millisecond. In Okay, in the A part, this is not the value, this is the mathematical expression, but in the E part, we have to find the proper value of the VC at t is equal to 20 millisecond. Okay, so let's see. This is the solution. First of all, we have to find the tau, which is equal to RC. The R is given, that is the 8 kilo, and C is 4 microfarad. So after multiplying, we will get 32 millisecond. Okay, now the VC is equal to E for the charging phase 1 minus e minus t by tau. Putting the values, we will get, this is the general expression in term of t. Now IC, E by R, e raised to power minus t by tau. Putting the values, you will get this expression in milliamperes. And similarly for the VR in the charging phase, you will get this. Okay, now the plots, this is the VC versus the tau, time constant, 1 tau, 2 tau, 3 tau. So for the 1 tau, you have to put t is equal to 1 tau over here. So you will get 25.28. Similarly for the 2 tau, we will put t is equal to 2 tau. 2 multiplied by 32 means 64. So we will get 34. So for similarly for the 3 tau, for the 4 tau, and for the 5 tau, we have to find till the 5 tau, because the capacitor is will be fully charged at 5 tau. So we have to find the VC. We have to plot the VC versus the tau up to the 5 tau. Now the VC versus the time. Okay, so this is the rising, exponentially rising curve, and this is versus tau versus t in milliseconds. So 32 millisecond, which is 1 tau. So if you locate, if you want to locate the tau's values over there, so we will find that 1 tau is somewhere here and 2 tau is 64, so it will be in between the 50 and the 100 milliseconds. Okay, similarly 3 tau, the 4 tau, and the 5 tau, but uh, we are demanded the plot for the VC versus the T, not the tau. In the tau, we have already defined it. Okay, now the current for the RC in charging phase is the exponentially decaying graph. Okay, and this is versus the time constant for the 1 tau. Putting the values, t is equal to 1 tau, we will get how much? 1.84. Similarly 0.68 for the 2 tau, and t is equal to 3 tau, you will get this. The tau value is 32 millisecond. Okay, now this is the VR, which is also exponentially decaying graph. Okay, so for t is equal to 20 millisecond, we have to find the VC. So putting t is equal to 20 millisecond over here, we will get 18.6. Okay, if you want to locate this, so here at t is equal to 20 millisecond, the value is how much? 18.6. Okay, 18.6 at t is equal to 20 millisecond. Okay, assuming a full charge in 5 tau constant. So for the capacitor will be fully charged at 5 tau. So 5 into tau value is 32. So we will get this 0.16 second. Now the charge, you have to find the charge Q is equal to CV. C is given, that is 4, and the voltage after fully charged we will get the voltage of 40 volt, which is the same as the source voltage. Okay, so after multiplying we will get 160 microcoulomb. Now we have to find the time in hours taken by this capacitor to be fully charged. So I is equal to, if we have the leakage, if there is a leakage, and the due to the resistance of leakage resistance of 10,000 mega, okay, mega ohm. So putting the values over here, I according to the Ohm law, I is equal to V by R. V is 40 and R is given leakage resistance 10,000 mega. So we'll get 4 nano ampere. Now, as we know that T is equal to Q or I, so Q is 160 from here and I is 4 nano from here. We will get, okay, now this is in seconds. So can by if you want to convert this time in hours, we will divide it by 3600. So we will get 11.11 in hours. Okay, now this is the circuit for the discharge phase. First of all, we have to charge the capacitor. For this purpose we have to move the switch to the position number 1. Okay, after once the capacitor is fully charged, so we will move the switch from 1 to position number 2. Okay, so now when the switch is moved to position number 2, the source will be cut off, so we'll have only a resistor and a fully charged capacitor. Now this is the isolated circuit when the switch is moved to position number 2. Okay, so here we can see that now we have a capacitor which was fully charged from the source. Then now this fully charged capacitor will act as a source for this drop R. Now R is the only drop. When circuit was at position number 1, we have two drops. The capacitor was acts as a load because it was charging, but now this fully charged capacitor acts as a source, not the load. Okay, so this capacitor will provide a voltage source for this resistor. Okay, so now when the switch was at position number 1, this the current was flowing like this in the clockwise direction, but now as this is the positive charge plate and the downward is the negative charge plate, so similar to the convention for this voltage source, now the current will flowing in the anti-clockwise, the counterclockwise direction, because this is a positive uh, terminal and this is the negative terminal. Okay, so the current will be in the counterclockwise direction, opposite to that when it was in position number 1. Okay, so okay, now there's a mistake, the position, okay, minus and minus. Okay, because at that position the polarity for the voltage drop was plus minus, but now the left side is minus and the right is plus. So the polarity is opposite because the current flowing through the resistor in position number 1 was like this. So polarity was plus minus, but now the current is flowing in opposite directions. That is why the polarity of the voltage drop will also be reversed. So this will be positive, this will be negative. That is why we have to put minus with the sign because the polarity is now changed. Okay, and similarly the current direction is also reversed, so we have to write a negative sign with this formula. Okay, the time constant is this similar as it was in the charging phase, which is equal to R multiplied by C. Okay, now we have the exponentially decaying graph for the voltage across the capacitor, because now it is acts as a source, and the energy of this capacitor is now dropped in the form of this load resistor. So that is why with the passage of time, the the capacitor is going to discharge and the voltage will be exponentially decaying. So e raised power minus t by tau. Okay, now the same current, which the amount of the current is same as it was in switch number one, but the only difference is its direction. Okay, similarly the voltage drop is the same as it was in position number one, but the polarity is reversed. Okay, so this is the charging phase when the switch was in position number one. Okay, so the capacitor was charging exponentially rising curve, and when it was moved to position number two, now the the discharge phase is started. So we will have exponentially decaying graph for the capacitor. Similarly, when position number one, again charging, again discharging. Okay, the current is starts from maximum, and it reduces to zero till the end of the position number one. When move to position number two, we will have this same magnitude of current as it was in position number one, but the the direction is reverse. So that is why it will start from here and also move to zero after a 5 tau constant. Okay, again this, and we are in charging phase is exponentially decaying, and now exponentially rising in the reverse direction minus e. Okay, because the polarity is reversed. Okay. A simple example for the discharge phase, using the example in 10.6, plot the waveform for VC and IC resulting from switching between contacts 1 and 2 in figure 10.39. Okay, tau is the same 32. Okay, now we have to use that same circuit, but now for position number 2. Okay, so the discharge phase, the formulas are, we have discussed the formulas from in this slide. So just putting the values, we will get VC is equal to 40, and this is the general expression in term of t. I minus 5, the minus represent the reversal of current, and the value is in term of t, so it means it is expression, we are expression. Okay, and we should also write a minus over here because of the reverse polarity. Okay, so charging, discharging, charging, discharging. Okay, again charging, discharging phase, charging phase. Okay, this is the response of tau. uh, it means if the R and the C values are changing, so the, the time required for any capacitor to completely charge or discharge will also be uh, affected. Okay, in this case, if we have tau is equal to 32 millisecond, so it will take a large time for to charge or to discharge, completely discharge. Now, if we have reduced the tau to 10 milliseconds, so it means the 5 tau will reach in 40 millisecond. In that case, the 5 tau was reached in 160 millisecond, but in this case, 5 tau is reached to 40 millisecond. Okay, so now the time required for any capacitor to completely charge or discharge has now been reduced. Okay, you can compare. In 160 millisecond, it was only charged, but now in 160 second, the capacitor has been charged and completely discharged twice a time. Okay, and this is the case for the IC. Now the example, when the switch is moved to position number 1, we have to find the expression, mathematical expression for VC, IC. Okay, and now when the switch is moved to position number 2 at 10 millisecond. Okay, so what will happen then when the switch is moved to position number 2 and when it is moved to position number 3 at t to 20 millisecond. Okay, and we have to plot the graphs for each of the part A, B, and C. Okay, the A is the same as we have discussed earlier, the charging phase. Okay, the new thing is the point to position number 2. When it is moved to position number 2, it is neither connected to the source nor connected to the drop. So it means there will be no charging, no discharging. So it means it is a storage phase. Okay, and it stores it, keep this the charge storage, which was stored in position number 1. So it will uh, keep it for uh, for position number 2 until and unless it is moved to position number 3. Okay, so A part is charging phase. Using the formula for the charger, only R1 is involved when it is moved to position number 1. When it will be moved to position number 3, now two resistors will be involved and these two will be in series, so we will use R1 plus R2 then. Okay, now R1 only. Okay, storage phase after 10 millisecond, putting the values of 10 over here, so we will get 12 as the tau is 1 millisecond, so it means the capacitor is fully charged up to in 5 milliseconds. 5 tau means 5 millisecond, and now the we have the switch is moved to position number 2 after 10 tau. 10 millisecond means 10 tau, so a lot of time has been passed. Okay, so it means it retained the charge as it was stored in position number 1. In position number 1 it was stored to 12 volt, so it will retain it in position number 2. Okay, now move to position number 3. So discharge phase will be start using 20 millisecond. Okay, so putting the values. Okay, first of all we have to find the new tau for position number 3, because now we have R1 plus R2. Okay, in series. So the new tau is tau dash, which is equal to 1.5 millisecond. Okay, using the formulas for the discharge phase, so we will get this. Okay, charging, storage, retentivity, storage, and then the discharge. Okay, charging, storage. In storage no current is flowing, so no current will be 0, and then the discharge phase. Okay, okay, now this is an example which is very similar to the previous one. Okay, so now this will be homework for you people. Position number 1, charging. Okay, so R1 and R3 is involved in charging phase. Now when move to position number 2, we will find a new tau. Okay, for position number 2. So now then R2 and R3 will be in series. The only difference is will be in the tau and the charging and discharging formulas. So this is a solved example for new people. Okay, now okay, let me discuss one thing. The switch is moved to position number 2 after after ta after one ta. It means the switch has not been placed for in position number 2 for the complete 5 ta time. It means the switch is moved to position number 1 at t is equal to 0 after 1 ta time. The switch is moved to position number 2. It means we, we doesn't allow the switch to be remain for uh, 5 tau. It means the capacitor has not been fully charged because the switch is moved to position number 2 after 1 tau, and we know that the capacitor will be fully charged at t is equal to 5 tau. So it means uh, in the incomplete time path, the capacitor has been moved to position number 2. So the capacitor will not be fully charged because the switch has been moved to position number 2 after t is equal to 1 tau. Okay, so okay, R1 plus R3 is involved in charging phase. Let us discuss it. So we will get tau is equal to 80 millisecond. Okay, now putting the values of charging, we will get this. Tau value is 80 millisecond. Okay, now uh, now the switch is moved to position number 2 at t is equal to 1 tau time. Okay, so after 1 tau, 63.2% of its final value, we will get 63.2% of its final value. So the total value is 20 volt. Okay, if it was remain for 5 tau, you will get 20 volt, but now after 1 tau you will get 63.2% of its final value. So 63.2% of 20 will be 12.64. Okay, now that capacitor will be charged up to 12.64. Okay, how to find this? Just putting the values over here. Instead of uh, t, put t is equal to 1 tau. 1 tau is how much? Tau is 80 millisecond. Okay, so we will get tau will be cancelled with this tau. 80 divided by 80, we will get e raised to the power minus 1, and e raised to the power minus 1 is 0.368. 1 was 0.368, 0.632 multiplied by the 20. So it means 0.632 means 63.2% of its final value. So okay, that will be 12.64. Now the tau dash for the discharge phase, we will get 80 millisecond because R2 and R3 are now involved. Okay, so using the discharge formula for the VC, putting the values, we will get tau value is now 40 millisecond. Okay, and 12.64 instead of E. Okay, instead of E, we will get 12.64. Here is the plot also showing the same story, that the capacitor was charging when it is moved to position number 0, sorry, position number 1 at t is equal to 0 second. Okay, the capacitor was charging, but now when after the 1 tau, the switch has been moved to position number 2, so the discharge phase will start, and these dotted lines shows that if the capacitor if the switch was kept up till the 5 tau, then the plot will be just like that. Okay, but now the scenario is opposite to that, and the switch has been moved to position number 2 after 1 tau time. So we will get this graph. Okay, charging, and then the discharging will be start right after the 5 tau, sorry, 1 tau time. Okay, we will get this, and the current for the discharge phase is reduce this. Okay, okay, no, sorry, for the charging, and for the discharging this. Okay, for the discharging 40 millisecond. This is the discharging phase current, and this is the charging phase current. Okay, and the current will be this, like this. After 1 tau, the discharge phase has been started, this. Okay, okay, thank you for the moment. uh, we will discuss the initial value in the next lecture.